Hey guys, how you doing? And it's Jalaj Aura here again, back with another video from BHM at GCSE Chem. And today is going to be, obviously the next section, C3.2 Atoms into Ions. So that's the section I'll be covering. The book I'm using is this one. It's the GCSE AQA Chemistry or AQA GCSE Chemistry Caboodle revision guide. And and so by the way, yesterday I was able to update everything on my website, put all the links to all the videos covered so far, the ones that I didn't do, like the remaining of chapter 2 and also C3.1 I was able to put up on the website, so it's now fully up to date till now. And I'll hopefully also be able to put C3.2 up there after this video, obviously, on my website. So yeah, sorry for the delay. Sorry for the delay again. Not being able to post it, not being able to kind of update it for the last few days. But yeah, now it's all up to date. And as I said, today we're doing C3.2, which is atoms into ions. It's a very interesting topic, and again, I've got some paper here because I'll be doing, I think, what a noise there, but I'll be doing basically a drawing and a drawing for a question of electron structures, so I need to show you that. But yeah, without further ado, let's get into the video and let's get into the section C3.2 Atoms into Ions. And if you're following the student book, which is obviously the big book, it's pages 38 to 39. So yeah, pages 38 to 39 of the student book. Let me just see if is this better for me or that much. I can't really see the textbook much. I think this is better for me. Yeah. So let's start. Let's begin. Sorry if my face gets hidden sometimes. But when two or more elements, sorry, if my face disappears, I should say. So when two or more elements react together, compounds are formed. We know that. We learnt that in chapter 1. We know that when elements react together, we form compounds. Now, the atoms of elements join together by sharing electrons or by transferring electrons to achieve stable electronic structures. Yeah, I've talked about this before. So basically, all elements apart from group 0, which are the noble gases, because they already have stable electron configurations. All the other elements in the periodic table basically react in order to have form, in order to obtain stable electronic configurations. Like noble gases, because if you have if you have completely filled electronic configurations and very stable electronic configurations, it means it becomes very stable, kind of the element that forms an ion. So yeah, so we're going to get more into that soon, but so they want to achieve the stable electronic structures. Atoms of noble gases have stable electronic structures. So yeah, that's what I was saying there, basically. And then when atoms of non-metallic elements combine, when atoms of non-metallic elements join together, or you could say combine together. What? Wait, let me just say that again, sorry. When atoms of non-metallic elements join together, join together, I think is better, by sharing electrons, it is called covalent bonding. So that's what you call covalent bonding. Covalent bonding is between two non-metallic elements. I don't know. I don't think it has to be only two. It could be more than two, probably. Yeah, it can definitely be more than two, I'm pretty sure. But yeah, when atoms of non-metallic elements join together, then that's what you call that's what you call covalent bonding. The sharing of electrons, basically between non-metallic elements, that join together. So yeah, hopefully that makes sense. And this is called covalent bonding. So here's the first question: how can you tell that the compound H2O has covalent bonds? So obviously H2O is water, and that's a compound that contains only hydrogen atoms and oxygen atoms, so which are both non-metals. So both hydrogen and oxygen are non-metallic kind of elements. So, because we just learned that covalent bonding occurs between atoms of non-metallic elements. So that should be the answer, because, hydrogen and oxygen are basically non-metals. It's formed from non-metallic elements. Water is formed from non-metallic elements. That should be the answer. I'll just let you know if there's anything else to add on there. Yeah, compounds form from non-metals, or you can say non-metallic elements. Yeah, that's fine. Non-metals as well. That's fine. And then we're moving on to the fact that when metallic elements react with non-metals, when metallic elements react with non-metallic elements, they produce ionic compounds. Now the metal atoms lose electrons to form positive ions, and the atoms of non-metals gain electrons to form negative ions. We've actually gone through this before. Metal atoms lose electrons to form positive ions, also known as cations, and then non-metallic atoms of non-metals, or non-metallic elements, you can say, basically, or you can say atoms of non-metallic elements, basically they lose they gain electrons to form negative ions. So metals form positive ions, they're cations. Non-metals form negative ions, also known as anions, basically. Yeah. And so we've gone through this before in a previous section, I'm pretty sure. And the ions have the stable electronic configuration of a noble gas. Yeah. The oppositely charged ions attract each other in the ionic compound, and this is called ionic bonding. So when you're defining ionic bonding, you should say that it's the electrostatic attraction between oppositely charged ions. That's the kind of definition. Yeah. And it happens between metals and non-metals, so metallic elements and non-metallic elements. And if you had to define covalent bonding, we could say it's the type of bonding that occurs between non-metallic elements, and it involves the sharing of electrons in order to achieve a noble gas, stable, in order for each element to kind of achieve a noble gas configuration. Or you could say stable electronic configuration. You don't have to mention it that way. You could say stable electronic configuration. So that's basically the crux of the two definitions. That's basically what the main difference is between covalent bonding and ionic bonding. Covalent bonding happens between only non-metals and involves the sharing of electrons, whereas ionic bonding, it occurs between metals and non-metals. And that involves obviously the transfer of electrons from metal to non-metal, from the metal atom to the non-metal atom. Basically, that makes sense, hopefully. Here's another question. So, which of these compounds have ionic bonding? So the compounds are potassium bromide, KBr, hydrochloric acid, HCl, hydrogen disulfide, I don't know, it's H2S basically, and then there's Na2O. If I'm not sure about the compound name, I won't say it. Na2O, and then Cl2O, and then obviously magnesium oxide, MgO. So I'm not sure about a couple of them, but basically, because we haven't covered that thing in A level as well, we don't really cover naming certain compounds, specific compounds like these in A level either. So I'm not sure about some of them. But basically the answer should be KBr, just to make myself clear. So KBr, Na2O and MgO. So because obviously with the metal and the non-metal thing that we've talked about before, so ionic bonding requires there to be a metal atom and a non-metal atom basically attracting, reacting together to form ions. So hopefully that is what the answer says, what the book says as well. Yeah, KBr, Na2O and MgO. I'm pretty sure I said that. And then, now we move on to the fact that elements in group 1 of the periodic table have atoms with one electron in the highest energy level or outer shell. Sodium atoms have an electron configuration or electronic structure of 281. So 2, 8, 1. I've gone through this before, so it's just a very basic recap because I've gone through this very quickly. That's why I'm going through it quite quickly. Forms sodium ions Na+ with the electronic structure 2,8. Now I might just go through this part a bit more slowly, because what it's essentially saying is, because we know group 1 elements have one electron in that highest energy level or their outer shell. We've gone through that before. The group number dictates basically, or tells you how many electrons there are in the outer shell or outer energy level, or in the valence shell as well, you could say. And basically, because they have one electron in their outer shell, they want to lose that one electron when they react with non-metallic elements by when they ionically bond or during ionic bonding. So if sodium has an electronic configuration of 2, 8, 1, it wants to lose that one electron to form to have an electronic configuration of 2, 8. So hopefully that makes sense, because if it loses that electron in its third shell, that outer electron, then it will just have an electron configuration of a noble gas neon. That would be 2,8 would be neon, but you won't classify as neon. You just say Na plus because it's lost one electron. So it's got nothing to do with neon, other than that it's got the same electron configuration as neon. Hopefully that makes sense. Na plus would be the same as the electron configuration of neon, but you won't mention neon. You just say now it's lost an electron, so it just forms an Na plus ion, because obviously because it's lost an electron, it has one more proton than it has electrons, so one more positive charge than negative charge, so basically Na plus. And we don't say 1 plus. Whenever there's 1, we always say Na plus, or we could say Cl minus. We don't say Cl1 minus, Na 1 plus. So hopefully that makes sense. Elements in group 7 of the periodic table have atoms with 7 electrons in their outer shell. If I didn't mention before, that it's important to say they have atoms. Sodium, the elements in group 1 have atoms that have 1 electron in the outer shell, because it's the atoms that have the electrons, not the kind of elements. It's important to say atoms. So so hopefully that makes sense. And elements in group 7 of the periodic table have atoms with 7 electrons in their highest occupied energy level or outer shell. And so, for example, chlorine's electron configuration is 2, 8, 7. That's just from the periodic table with atomic number 17, so it has 17 protons and 17 electrons, so it'd be 2, 8, 7. And because the third shell can have 8, it'd want to actually gain an electron to form Cl minus, so chloride ion Cl minus, so it can then form 288, which is actually the electronic configuration of argon, of neutral argon. But chlorine and Cl minus and argon are very different from each other. It's just that the electronic configurations would be the same. But what I'm trying to say is basically when atoms lose or gain electrons, they form stable electronic configurations of similar to that of a noble gas. So hopefully that makes sense. And basically here's a diagram that I will quickly talk through. So hopefully you can see this diagram here. Now we'll talk through that with the shells and stuff. So basically what we have is we have sodium and we have chlorine. So we draw their electronic structures. And when we're drawing dot and cross diagrams, what we could do basically is we can only show the outer electrons. Most of the time we do that. So if we're showing the outer electrons, we can represent, for example, represent sodium by a cross, and then chlorine would be represented by dots, because it's either dots or crosses. So you do that, and then that goes to Na plus, because now sodium loses its electron. So hopefully I don't know if you can see in this little diagram, if I'm even showing it properly, Na plus, sorry, it has Na, has an electron, but now it doesn't have any electrons. So it's just got 2,8. First it was 2,8,1. But chlorine has now gained that electron. 2,8,7 goes to 2,8,8. And hopefully you can see one of the electrons is an X in the chloride ion. So that the Na plus and Cl minus are formed to form the table salt sodium chloride. And this, I think, is a much bigger version and a better version. If you were to draw out the whole kind of shells, the whole kind of configuration, you draw the whole configuration of sodium, you do the same for chlorine, and then you basically do square brackets with what the ion configurations would be. They should be relatively straightforward, because you're just either losing an electron and then you're transferring an electron to another kind of non-metal to a non-metal. So hopefully that should make sense, because we've gone through electronic structures before. This is just with ions, by just losing or gaining electrons, so that shouldn't be very difficult at all. But if you do need to revise that, I'd recommend going through the student book. I think it explains it in much more detail. This obviously is for, you know, brief revision purposes only. So yeah, obviously here we have the dot and cross diagrams to show the electron transfer in sodium chloride NaCl. And here we have again the formation of sodium chloride NaCl as an example of an ion formation by transferring an electron. So hopefully that makes sense. And then you can also use dot and cross diagrams to show the electrons in the outer shells of atoms and ions involved in forming ionic bonds. So sometimes in exams they just they tell you to obviously draw using dot and cross diagrams, but what they tell you is that only you can draw the outer shells. So that you just need to draw the outer shells with how many electrons are on the outer shell, and then maybe the metal atom will lose an electron, which will be transferred to the non-metal atom. There is an example question on this, so I'll go through that. But yeah, the compound sodium chloride has equal numbers of sodium ions and chloride ions, so we write the formula as NaCl, because we have Na+, because it loses an electron. Chlorine forms Cl-, which gains an electron, so Na+ and Cl- gives NaCl. And because the plus and minus cancel each other out, and that's table salt. Now here's a question: draw a dot and cross diagram to show how the sodium atoms and chlorine atoms form ions. So I don't why have they done that again? That's so weird. Right. Okay, that's quite weird. They've actually, yeah. Okay, I'll do it quickly, but that's actually so weird. Basically, I'll quickly draw it again, how you would represent it, but that's so weird. They're asking the same question again and again, but... And then for chlorine, what I'd have is basically I'd have a chlorine here, and then another chlorine here, another chlorine here. 1, 2, 2. I'm not going to show you how I did this, because we've gone through electronic structures before. This should be very familiar to you actually. It's just a case of kind of electronic structures you need to learn for the exam. So, and then I'm obviously going to show the ions that it forms. That's so weird, because again, I'm just going through this very quickly because it is quite a basic topic. Not much, in my opinion, needed here. Actually, and then chlorine ion. Not much explanation required at all here. It should be a relatively straightforward topic actually. Sorry if the diagram gets a bit messy, I'm just trying to draw it very, very quickly indeed. Cl-. So this is basically what I've drawn. Hopefully you can see it. I've drawn the electronic configuration of sodium. I did the same for chlorine, and then I did the ions basically. And no, wait, one thing I forgot. No, wait, forget that, because I've done it wrong. Sodium should have been with the crosses that I drew, and basically. Wait, let me now correct this. Basically, I'm really, really sorry. I don't know why I'm in a hurry, but it's just trying to correct all this, basically, that mistake I've done. Just trying to really correct this mistake. I don't know what I did. Sorry, guys. Sorry, really, really sorry. Hopefully this makes sense. basically you should know how to draw electronic configurations, but and then obviously one electron, and then one electron that I'm showing here. So sodium I've drawn with crosses. The chlorine I drew with crosses, but it's actually meant to be dots, so which I've tried to do there. And then this is the sodium ion, Na+, which has lost an electron. Hopefully you can see that it has lost an electron. Yeah, because it's no longer got its third shell, as you can see. It's only got 2. Whereas chlorine, now ion, Cl-, as you can see, has now got 1 electron from the sodium. So you can see this X there. Hopefully, and then the dots are basically the the rest of it. So Na+ and Cl- gives NaCl. So hopefully that makes sense. Sorry if the writing's a bit kind of off. But yeah, hopefully that makes sense. And the synoptic link is you can read about the formation of ions in topic C1.7. We obviously went through that before in chapter 1. And then keywords are covalent bonding, ionic bonding, dot and cross diagram. So that's hopefully makes sense. That's good, hopefully. And then just to run over the key points, the elements react to form compounds by gaining or losing electrons or by sharing electrons. The elements in group 1 react with elements in group 7. As they react, atoms of group 1 elements can each use 1 electron to gain stable electronic configuration of a noble gas. The electron from the outer shell can be given to an atom of group 7. So basically, this is a bit of waffle, but basically what it's saying, like sodium and chlorine, sodium is in group 1, chlorine is in group 7. So sodium transfers one of its electrons, the outer electron, to chlorine. So the chlorine gains that electron, and both of them have now stable electronic configurations, like similar to that of a noble gas. Yeah, so that hopefully that makes sense, and they form ions Na+ and Cl-, but you could obviously have other ions as well. It doesn't have to be sodium and chlorine only, which we'll explore more later as well in the next video, I think. And so electronic structure of a noble gas, yeah, that's fine. The electron from the outer shell can be given to an atom from group 7, which then also achieves the stable electronic structure of a noble gas. So yeah, basically the group 1 achieves the stable. Group 1 ion obviously means that you group 1 atom becomes a positively charged ion, a cation, which means that it has a stable electronic configuration of noble gas, and the same goes for the negatively charged ion from group 7, basically. That's forms like chloride, or you can have bromide ions and stuff like that. And you have 1- ions for that and 1+ ions for group 1, and both of them would have stable electronic configurations, and then you can work out the formula of the compound, basically. So hopefully that makes sense. The dot and cross diagrams, the atoms into ions. This section is called C3.2 was atoms into ions, and hopefully it was really helpful. Sorry if you felt it was a bit rushed, but yeah, the video was getting quite long. It is quite long already. And tomorrow we're going to be going through C3.3, which is ionic bonding. And look, it's a very, very small section. And hopefully, if you didn't understand, well, hopefully you did understand. But if you do have some doubts, hopefully by tomorrow they'll be cleared, because tomorrow is also on ionic bonding. So we'll be going through that topic, revisiting it again in the next section. But hopefully you found this video helpful. I'll try and upload this. Obviously a video on my YouTube channel, and I'll try to post the link on my website as well. And yeah, make sure to share, like, and subscribe. Turn the notifications on if you haven't already, so you're notified and updated when I when I upload new videos that you can watch. And yeah, see you in the next video, guys. Thank you very much.